I am doing homework number 3, problem number 24. The problem says, what is the electric potential at the dot? So I drew out the diagram here. You see it has 3 point charges. Here's the point that we need to know the electric potential for. We see the distance from here to here is 4, here to here is 3, and we know the 3 charges at each of these points. And I wrote down the equation for electric potential here. It's U equals KQ over R. So in order to solve this problem, we need to know what we know and what we don't know. We know K is a constant, so we know that. We know Q, which is these individual charges, so we know that. And we know the R for 2 of these charges. So R from this point over here to the dot will be 3 centimeters. And from here to here will be 4 centimeters. But we also need to know the distance from this point to the dot here. And the way we do that is we use a right triangle here. So we know that Pythagorean theorem states that 3 squared plus 4 squared will give you this side squared. Or if you want to use that shortcut, you know that a side with 3, 4 will give you a distance of 5 centimeters this way. So now that we know R, the next thing we need to know is that you have to use the principle of superposition for this, which means that you have to consider each of these charges individually and to determine the net effect that it has on this dot. So if we start with this first, we know that K is 8.99 times 10 to the power of 9 nm squared over c squared. The charge is 2nc, but we need that in coulombs only. And we know there's 10 to the power of 9 nanocoulombs in 1 coulomb. This way the nanocoulombs cancel out, and you have c's cancel out with only 1 c remaining on the top. And you divide that all by the distance from here to here, which in this case is 3 centimeters. And we also want that in meters. So we know there's 100 centimeters in 1 meter. If we do all of that, we find that the electric potential from on this part to this part is 599.33 volts. Alright, next, let's consider this part onto this part. So we do the same thing. We know K. And the charge is still 2 nanocoulombs. So if we convert that to coulombs, it's 10 to the power of 9 again. And the distance on the bottom will be 4 centimeters instead of 3 like last time. And you want to convert that to meters again. So 100 centimeters is 1 meter. And if you plug that into your calculator, you will get 449.5 volts for that. And lastly, we know that the distance here is 5 because we found that before. So we do the same procedure again. The value of K. This time our charge is 4 nanocoulombs. 10 to the power of 9 again. And divide that by 5 centimeters now. Convert that to meters again, so you divide by 100. And if you plug that all into your calculator, you will get 719.2 volts. So the principle of superposition says you have to consider each of these effect on each other individually on the point here. So we found that the electric potentials at each of these points are these following values. So in order to find the net electric potential at this point, we have to add up all of these voltages that we found. So if we do that, we do 599.33 volts plus 449.5 volts plus 719.2 volts. And that will give you a total of 1768.03 volts. And if we do significant figures, we say that is 1.8 times 10 to the power of 3 volts. That is our answer, and that tells us the electric potential that is at the dot because of these 3 charges acting on it.